So in noise, you may have various noise are there. So it is not only noise coming from environment, but there are noise which are inherently available in particular device. Those some of the noise names I can tell you. Maybe explanation will be part of some other course. It's called thermal noise. You may have flicker noise. Some of the noises are known as color noise. Some noise are known as white noise. Do you understand? Have you ever heard this word, white and color noise? So white noise, we know that white spectrum has like every color is there, right? So white noise is the one which has noise available at every frequency, and color noise is the one which is available at particular frequency. So generally we are saying that this particular circuit is having colored noise at, let's say, 1 megahertz or sometime 1 kilohertz, means at that particular frequency I am seeing the noise or some unwanted signal. So that is what noise is, and these are known as basically device noise, what I told, thermal noise, or some noise are highly stochastic and you cannot predict them. Those noises are like popcorn noise, so they are bursting and they are also known as burst noise. So those are going to distract your signal. uh, have you ever done DFT or discrete Fourier transform? You did it, okay. Just for your, just to know whether you know or not, if there is a sine wave with frequency of 1 megahertz, just assume that you never seen such instrument, but that instrument name is spectrum analyzer, whose uh, function is to convert your time signal to frequency. So it will display everything with respect to frequency. That instrument is known as spectrum analyzer. So if it is displaying with respect to time, it's known as DSO or CRO. But the one which is displaying with frequency, it's known as spectrum analyzer. So if it is sine wave with 1 megahertz, I am generating from a function generator. What are you going to see in this spectrum analyzer? What do you think? 1 megahertz and 1 volt. Are you following my question? What I mean to say? No, Divya. So I'm saying that when you studied signals and system, you may have learned something called spectrum of sine wave or sine wave with 1 megahertz 1 volt. If I want to convert it to a frequency signal, how will how will it look like with respect to frequency? Have you done it, right? Believe me, this is like all the companies, if you are in electrical engineering or electronics engineering, all the companies are going to ask you this question for sure. Excellent. So one impulse at omega and one impulse at minus omega, and that omega in our case it's 1 mega, right? So I'm drawing in terms of hertz, so it will be 1 mega and minus 1 mega, although we are not interested in minus side, right? So this will be 1 volt, right? Or you can say that 0 dB. So that is what my spectrum analyzer will show you. But spectrum analyzer is the real thing, and this was on paper. So when you are saying that at 1 megahertz there is some impulse, otherwise other places it's 0, but that is not the case, and 0 in dB scale is not available. So in spectrum analyzer, here it's in decibel, so 0 is not available anywhere. Can you understand? On log scale, 0 is not available. There might be 10 raised to minus 9, 10 raised to minus 20. It can you can make it close to 0, but you cannot have 0. So if it is 10 raised to minus 8, it's minus 180 dB. This will be minus 240 dB, right? So here spectrum analyzer has to show something at some frequent like till some value only. So you will see that it's generally at minus 100 dB. This is a limitation of, because this is an instrument, it's not real thing. Sorry, it's a real thing, it's not something on notebook. So you will see that there are many other, unwanted, these impulses are impulses are actually available. These impulses are the harmonics, right? So this may be first harmonic, second harmonic, third harmonic, all are there, and these are coming from, this is known as noise floor, and this is known as signal. And there is very important term, in future you are going to see that, the signal to noise ratio, or the SNR. So noise has to be as low as possible, and signal has to be as high as possible, but in reality it will be difficult. So that is what we want to do the simulation, that is known as noise. So if you are interested in such kind of, like, this is a big study generally. To understand noise you need to take even, complete course on noise. This is a big thing, people are doing even PhD on noise. So it's not small thing to do it in maybe in 5 minutes, but you can learn it maybe in other course, maybe in many courses you will learn noise in different forms. Maybe in communication different noise, power in different, analog in different, everywhere noise will be there but in different form. So you'll study that. If you are interested in just DC transfer, means at zero frequency you want to learn it, you want to do that, but DC with small signal. Now you understand what is small signal, right? Small signal is the one which will not saturate the output. Your input is small enough, and I want to see its average out value, what is the output. So then I will take DC transfer. Similar to that, you may have DC bias point. You some analysis are also adding something called operating point or Q point. All are synonyms, or all are coming under this category. DC bias point means I want to see how much DC value will be available at different points. Let's say this point, I know that it's 0 volt, but whether it's 0 volt or not, if I want to do the analysis, it has to be annotated on schematic itself. So those kind of analysis, we are going to call it DC analysis, and that is the first analysis people are going to do if they are making some amplifier circuit, or using BJT. Whatever BJT maybe you have made it in, like, in your IC161 course, same amplifier you can make it here using the name of same BJT and giving the parameters. You will see the same response which you have seen it in DSO. You have to add those noise and everything, so everything will be similar to what you have seen, right? You can add also similar DSO, everything you can add. So as I told you, I'm interested in finding out the AC analysis. AC is the one which is going to give me the transfer function. I'm going to use decade as nature of the sweep. Means x-axis will be in, if you remember, we used to use semi-log paper, so it will be in decade. Number of points per decade, let's assume that 100. Start frequency I'm taking 1. Remember, do not give 0 as start frequency, because on log scale you will never have 0, right? You already know this. You can give 10 raised to minus 6, 5 or anything, but 0 will not be available. So I generally start with 1, right? And you can give as high as whatever you like. Let's assume 1 giga I'm giving. So here you can see that there is some explicitly some command is automatically written. This is called .ac. .ac will tell you that this is AC analysis. If I want to do transient, it's known as .tran. For DC, it's .dc, .noise. Sometimes pole zero analysis is also being done with known as .pz. So all will have some commands with, like, I have to use decade. I have to, per decade you will have 100 points, and the analysis is from 1 to 1 giga. and that will be, I kept it here so that my simulator know that he has to do the AC analysis, right? And then you can do this run command. If you are doing this run, you will have some waveform window. Now I want to see the output. So if this waveform window is open, then you can go to your schematic and you can see there is something called, you have the positive end of the multimeter is in your hand, right? So if I keep it here, the red color, so if I press it, I can see the magnitude as well as phase response. You can find out how it's happening, all this frequency response. You can look at the transfer function and you can see that, and you can observe how this phase and magnitude is happening. But the most important part, as I told you, the simulator is not simulating this circuit, but it's simulating something called netlist. So netlist is very easy. Netlist is the one which will tell you how these components are connected. Remember, all these components are defined in the library. It's in the library, right? So let's assume that I want to write down the netlist for this kind of circuit. You can see here I can name every node. So this node, let's call it 1, let's call this node as 2, and this node as 0, right? So if I want to start with, like, I can start with any point, it's not a problem. You can write down capacitor first, resistor first, or voltage first. But let's assume that you want to write down, or starting with resistance, so you have to write down the resistor. Let's name it R. So I name it R1. Then its value is 1 kilo, so I'm going to write down 1 kilo. It is between 1 and 2 nodes, so I'm going to write down 1, 2. So automatically it will create resistance between 1 and 2. Similar to that, capacitor, it might be 1 micro between 2 and 0, and voltage, let's call V, whose value is 5 volt, and which is between 1 and 0. If I am writing this, this is known as netlist, and it creates this particular circuit. The only thing is how to write, like, it has to run some analysis. So if it is AC analysis which I want to run, I'm going to write down dot AC. Maybe I need decade or octave, whatever, like, thing you want at x-axis, you have to write down. Then I'm going to start, or 100 points per decade, and I'm going to start with 1 to 1 giga. Right? It is much faster than what you have done it in the schematic, right? And to change these values and all in text file is much easier. The only thing is here, if it is resistor, capacitor, voltage, all these are considered as something called kind of ideal library. So till ideal library, there is no problem. The problem occur when you want to add, let's say, BJT, because BJT has to come from some specific made, some number with N or something will be there, then diode, or maybe op amp, it might be 741 or whatever the number is. So then you need to know how this op amp or how this BJT or how this diode will work. So those things needs to be added here, and that is known as model library. If you remember, I told you once that there is only one company in the world who is making all this model, which is known as BSIM. BSIM is Berkeley Simulator Model. So Berkeley is same as UCB, if you know, right? Others are also there, like some models like Philips also making the model, but those are specific to MOS, right? MOSFETs. But you need to add those model libraries, or you have to define the path where it's written there. This is BJT, and all these values are stored somewhere. Like if it is MOSFET, then MOSFET will have equation which is ID, mu, and Cox. W by L to VGS minus VTH whole square. This is the device equation you are going to study in sixth semester. Yes, fifth semester. If you are taking that there is one course called Device Electronics for Integrated Circuits. So in that course, you are going to study this equation. So if this is gate, this is drain, and this is source, the drain current is equal to mu n, which is mobility, oxide capacitance. So all these values has to be stored somewhere. So these are the values which is coming from the device. When I'm saying device, it's because of how you are doping particular n-type, p-type semiconductor. All these things are device properties which cannot be given by the user. User can give width and length. So that will be outside, which you can uh, tune it here and there. But these values has to be defined somewhere. Means it will be in model library. You need to add that path. So as I told you, here all these op-amp and everything like LT1058. So this op-amp is defined somewhere. Right now we took from here component. So it is given in some uh, place which is users Hitesh library, right? So it is defined there. But in reality, you need to give the path in netlist. So if you look at the netlist, so view spice netlist, which looks like this one, where you have resistance to node values and its own value, and then different voltage sources V1, V2, V3, and XU1. This is this op amp whose model library is defined somewhere here. So that is how netlist can be written. So at the first end, what I'm suggesting, whatever the project I'm going to give you, I'm going to write it today evening. So whatever the project I'm going to give you, you make the schematic and look at the netlist also and try to understand how the netlist has been written. It's not so much complicated. You look at that, try to understand it so that in future you can use it, right? So if somebody will show you the netlist, at least it should have known to you. In power electronics course, Ramesh Orgundi sir is teaching this. I talked to him and he told me that he is teaching netlist also. So some advanced level of netlist, if you want to explore, then you can do that in some power electronics course in future, like maybe in your sixth semester one course is there, right? So there also you can learn more, but now you can start with like some netlist, right? So like most of the things are recorded. It's all about how you are doing on your own. If you are like just watching the video, then you will never learn it. You have to do it with your own hand, right? Then you will learn it, right? So mostly what I'm going to give you some filter circuits with resistor capacitor around op amp. You have to write one page of report where you are going to keep this schematic, this waveform window, and you have to explain its working. I don't know what circuit I am going to give you, but you have to find out the functionality of the circuit from the waveform. For that, you might need transient, you might need DC, or you want to do all the analysis. In that case, like number of pages will increase. Just like this simulator will do all those things. Right? This is what I want you to do. So now what I want to start with is filter design. So for this particular course, that's the last topic. So as per your course curriculum, it has been given 3 lectures. So I think I can cover it in 3 lectures, or I'll cover till the point where I can cover on the basis of your understanding. Because there is, in connection with this particular thing, there is one course which is called DSP. So now You can take all the courses without you know like there is nothing which is not covered in the course, which is not like which is not going to be useful, right? So those are not useful. I have not covered. Like polyphase circuit, it will be start from zero in other course. If you want to go for polyphase means power electronics, it will be covering there. So its prerequisite is not required. Rest of the things I covered everything. Right? There is no not a single topic which has not been covered in the course. All the courses, all the things have been covered already. So in filter design, I might use not only passive filters, but I'm going to use active also. When I'm saying active, I'm going to use an op amp. So generally, we need to understand following things to understand the filter. So you need to understand the filter characteristic. Some of the things like band pass and low pass, all these classification and their characteristic is already known to you. Even their transfer functions are also known to you, and you understand. When I'm saying sensitivity problem means if there are some of the components like R, L, and C, if I am changing those elements, how much my transfer function is sensitive, because some of the components are there. If I'm changing from 1 millihenry to 1.01 millihenry, and the entire thing change. So if particular transfer function is so much sensitive to particular device, you need to make sure that you have to address that problem, and you have to make the transfer function such that the sensitivity problem will be lesser, or it will be distributed among all the particular components. Next thing is active filters. So as like we have studied Foster, Coyer, and other techniques. Similar to that, we can have Selen and Key filter. So Selen and Key both are name of the scientists. So you have to keep them in capital. So Selen and Key. Then you may have KH and biquad. So when there is a biquad is very famous topology of filter, which is actually biquadratic filter, which follows the the quadratic equation. So that's why it's a biquad, and in short form, people are calling it biquad. And thereafter, as I told you, this active filter may not have all the unique solution. Just to make a unique solution, you may have some approximation for filter response. Those might be Butterworth, Chebyshev, Basel. You heard about this? Yeah, maybe elliptic. So different approximations are there. Although these approximations are not in our course, it's Butterworth and Chebyshev approximation. So these approximations are telling you how your response should look like, right? So I'll try to cover one by one. It's one of the most interesting topic of electrical engineering. This is what I feel. Okay, and I'm going to follow this book. Okay, please follow this book. Believe me, like I'm giving this statement to many people that if you are reading this book, maybe you will change your interest of your subject to analog. This book is very nicely written. But if you are reading any other book, there are many books. I don't want to criticize any book, but there are many books through which, if you are studying that those topics, then you will never like analog. So this is, by the way, this topic is coming under analog, but the concepts can be like useful for DSP or other subjects also. Okay, so filter characteristic. If we are interested in low pass, you must have seen such kind of characteristic where you have flat response at low frequency, and after that there is a transition, maybe minus 20 dB per decade, minus 40 dB per decade. That will decide the order of your system, right? So this is already known to you. But as this order is increasing, or as you are keeping the poles and zeros at particular location, this might change the response. So it may not be flat at these two particular places, and you may have some transition band. We are going to call this transition band as roll off, and this is pass band ripple and stop band ripple. Even though you want to make flat response, this is the ideal thing, as you are increasing the order, and if you are keeping the poles and zeros at particular location, you will have some ripple. If you remember, uh, if there is a second order system, we have found out that the response might be this one, or it may go to this one also. Means with single LC circuit also, if you place these polynomials such a way that output may be more than input. This is what we'll learn right at the beginning. If you have complex and conjugate pairs of uh, poles, so V out by V in may be more than 0 dB. 0 dB means its V out is higher than V in. So this may happen at particular frequency. This is happening because of the LC tank and how you are keeping the its poles and zeros. So you can observe that. So similarly, when you are going to make even third order, fourth order, system will have here also some kind of ripples. So this is the reality. As you are increasing the order, you will have some more ripples. So pass band ripple, stop band ripple, and some roll off. So these things will be observed. So this is just for information that it's not a flat response which looks here in the left hand side figure. Classifications of filters. We already know that low pass, high pass, band pass, and band reject, or this is band stop, or this is also known as notch filter. Right? Three different filters I kept. So still we are moving with just passive component just to understand. So first one, can you tell me what kind of filter it is? Yeah, Rohit, what do you think? Do not try to remember. Try to solve this. So what is happening at low frequency? Hmm? So 0 volt, 1 volt, 2 volt, V out equal to V in. What is going to happen? V out equal to V in, or no, no, but how it's happening, you know about this. Okay. Even here you can see that its capacitor is DC blocking. On the low frequency, this will be blocked. This is what maybe Rohit was trying to do. So at the time, if you are having multimeter whose input impedance is infinity, then you are going. So if this is very high value, let's assuming infinity. So then it's, so you are going to see V out equal to V in that case only, right? So this is a low pass filter, and what is the order of this filter? Okay, first order, and the cutoff frequency is 1 by 2 pi R1C1 in hertz, right? What about this one? So you can write down here 1 by C1S plus 1 by C1S plus R1 on shunt with 1 by C2S. Can you find out this? What are you seeing? What is the final equation? By the way, all these slides have been copied from the book, so ebook, so which is Behzad Razavi. I'm only following one book, Behzad Razavi. How notch? High and low frequency will pass. Okay, so here this will block at DC. This will block V out equal to V in at low frequency. At high frequency, what is going to happen? C1 is also short. So depending on the value, look, how whichever will have the lower resistance or the lower impedance, that path will be taken, right? So you have to look at the value of C1 and C2. But before that, can we have this final equation? Yeah, Shashi? Yeah, Anvesh? Yeah. R1 C2S plus 1. R1 plus R1 plus R1 C1. R1 C1 plus R1 C2. Okay. Yeah. So it's not second order, by the way, right? But here there is a thing that this capacitor is connected between input and output. You can see it's connected between input and output. In that case, it creates a zero. So that is what created here, right? So similar to this, you can see you should have one more zero here also, right? It will be second order because capacitor and inductors are there. So it's effective. So it will be second order. So denominator you should see some highest order of 2, and here you should have 1 0. Second one. So you have to decide on the basis of values. You cannot tell right now. So that's the problem. So let's say there is one filter whose transfer function has two things. One is 0 and one is pole. If I am keeping 0 earlier than pole, and in one case I am keeping pole earlier than 0, then the characteristic change and the name of the filter will change. That's why I was not naming them. Right? So it's all depending on how you are keeping poles and 0 location. So it's in your hand to choose the value of R and C, or sometimes inductor also. Right? Just to give you one intuition, like all these things, whatever we are learning, this is addressing to uh, a technology for electronics where it will go to directly to the chip. If you are interested in making some IC of what you are doing, we are not going to use inductor inside this chip because it takes more area. Inductor can be made only with, like if you are making inductor on chip, it will also like this only. You have to make like this inductor. It's a spiral inductor, and that will takes lots of area. And if you are studying electromagnetic theory, you may notice that in this you will observe magnetic field also, and that magnetic field will disturb this small area of my IC. So rest of the things will be coupled with lots of unwanted series resistance or some parasitic capacitors. So I don't want that. So generally I am going to avoid inductor. If you are planning to be in communication or electronic side, you are going to avoid inductor. Inductor should not be there. I'll take 5 minutes more and then we'll say like off for today. Okay. So similar to that, this is the one kind of circuit. Can you tell me what is the transfer function? So by the way, this is inverting amplifier. If you remember, inverting amplifier with this configuration will give you minus RF by R1. Yeah, I can do this, right? Then I can find out the transfer function also. So definitely there is a path from input to output through capacitor. So there is effective two capacitors, but it's one capacitor. So you will have 1 0 for sure, right? So it's up to you how you are making it low pass or high pass, and through which you can make the circuit like as per your desired specifications. Now forget about other things which we have studied. Now go to the second order filters whose transfer function look like this one. If you are studying control, might be Q will be replaced with 1 by 2 zeta, by the way. In control, they don't use Q, they use zeta, which is known as damping ratio, and in rest of the places you will call this one as quality factor. But both are connected with this equation. Q is equal to 1 by 2 zeta, right? So if I want to find out the pole locations, where the pole locations will be, there are two poles. Then E square minus 4AC divided by 2A, right? So you will get this equation. Sorry? Minus B plus or minus B square minus 4AC divided by 2A. Am I making any mistake? Or? Hmm? Oh, 4AC. Okay, okay. You are saying this. Okay. Okay. So through that you can find out this equation, and you can find out that as you are increasing Q, this particular term will be lesser than 1, and you're going to make these poles exactly on j omega axis. If they are on j omega axis, it can be realized with which kind of circuit? Only with LC. If you are drawing its reactance curve, you will find out, right? So if you have the transfer function, you can find out with any technique like Foster Coir or any technique, and you can couple with or op amp. However, if it is not at j omega axis, it will be at other place where you will have some real part also there. And if this is, by the way, this has to be positive real function and it has to be realizable, then if you are seeing with partial fraction method, if they are coming all the negative residues, then it's RL impedance and RC admittance. If it's giving positive residues, we can find out RC impedance and RL admittance, right? So these are the properties through which you can design second order filters, and that is possible thing, right? Okay, this is already we studied in Bode plot, right? Okay, so we need to look at the place which is, this will give you 1 by root 2, this also give you 1 by root 2, this 1 by root 2 is going to give you 0.707, or it's equal to minus 3 dB, and that is why minus 3 dB is very important number, right? Minus 3 dB frequency, minus 3 dB bandwidth, it's coming from this. And if your quality factor is less than 1 by root 2, the system is like smoothly going towards a like higher frequency, so this is known as critical damped, right? And accordingly, like if it is so much lower than this, then it's over damped, and this one is under damped, because still you can observe some damping, right? So rest of the things we are going to talk maybe Thursday and Friday. So I'll try to cover as much I can cover. Yeah, somebody was saying something. Okay. Yeah, my by the way, I may ask in your exam paper of the end semester, I may ask net list of some circuit. Okay, so this will be surely there. At least one small question. Huh? There is no bonus. Bonus was already done, right? If I'll find out that you people are performing very poorly, then I'll increase marks automatically. For the paper, like it will not be 30 marks, it will be 35 marks. Just to make sure that you are reaching 30.